What's up, everybody? In this video, I'm going to explain USACO's 2019 December contest, silver level, problem number 3, milk visits. Farmer John is planning to build N, where N is between 1 and 10 to the 5th, farms that will be connected by N-1 roads, forming a tree, i.e. all farms are reachable from each other and there are no cycles. Real quick on that. So when you start adding farms, you always have one less road than you have farms. This tree structure is really important. It shows up in a lot of problems. So for example, if I have one farm, obviously I have no roads. If I had 2 farms, I'm only allowed to have 1 road. If I have a 3rd farm, I'm only allowed to have 2 roads. Every time I add a farm, I can only add 1 road, which means every time I add a farm, I have to connect it to something that already exists. Additionally, there are no unconnected farms. So I wouldn't be able to be allowed to put a farm here, then leave it unconnected, and then connect these two and make a circle. Every farm has to be connected, which means every farm you add gets 1 road to connect it to 1 existing node. When you follow this structure, what ends up happening is that, let me switch over to blank here. From any node to any other node, there's only one way to get there. So if I were to pick like node A and node B, there's exactly one path connecting node A and node B, and it's this right here. And no matter how many nodes I add, there will never become a different path connecting those 2 nodes. Those 2 nodes will always be connected by that exact same route. So basically that's your tree structure. No matter what you add, you can never have a cycle. And once a path is determined between 2 nodes, that path always stays the same. All right, let's back to the problem. Okay, so forming a, where is it? Each farm contains a cow whose breed is either Guernsey or Holstein. So every farm is gonna have exactly 1 cow. Farmer John's M friends, where M is between 1 and 10 to the 5th, often come to visit him. During a visit with friend I, so just for any given friend, Farmer John will walk with his friend along the unique path of roads from farm AI to BI. It may be the case that AI equals BI. So basically, we've got a starting farm and an ending farm for every single friend. So for friend I, we have a starting farm and an ending farm, and we're going to walk the path. And remember, there's exactly 1 path connecting those 2. Additionally, they can try some milk from any cow along the path they walk. Since most of Farmer John's friends are also farmers, they have very strong preferences regarding milk. Some of his friends will only drink Guernsey milk, while the remainder will only drink Holstein milk. Any of Farmer John's friends will only be happy if they can drink their preferred type of milk during their visit. So every friend has exactly 1 preferred type. So obviously they're not going to be happy if they are walking on a path that doesn't have their milk of preference. Please determine whether each friend will be happy after visiting. Scoring test cases 2 to 5 or n less than 10 to the 3rd, m less than 2 10 to the 3rd. So what this is about, just real briefly on complexity. If I have a bunch of farms that contain n farms, and then I want to do 1 walkthrough from some farm A to some farm B, and if I want to check all of the milk I encounter along the way, then this process of doing this search, since you don't know exactly where your target is, whether you do breadth first or depth first, you're in a complexity of approximately O to the n. And the reason why is because it's entirely possible that this farm is just an exact straight line, and the path is going to be from one end to the other, and you'll have to visit every single farm along the way. It's also possible that when it forks, you might go the wrong direction. So anyway, however many nodes you have, that's how much work it's going to take to do 1 single walkthrough. But the problem is we also have m walkthroughs. And since m is a maximum of 10 to the 5th, and n is a maximum of 10 to the 5th, if I do O of m times n, then I'm going to have 10 to the 10th, and 10 to the 10th is that big red flag number we don't want to hit. So what we have to do to make this work is we have to find some way that we can do some pre-computing such that when a person does a walkthrough, that we can figure out in less than O of n time whether or not they're going to get all of the milk that they want. Because we can't make m smaller. M is how many walkthroughs we have to do. We can't do fewer than all of them. But n is the amount of work it takes to find out whether or not they have milk along the path. And if we did some pre-computing, we might be able to avoid that n or make that n smaller. And that's exactly what we have to do for this. Okay, the input format is from the file milkvisits.in, with the first line containing 2 integers, n and m. Remember, n being how many farms there are, and also how many cows there are, and m being how many friends are coming to visit and how many paths are going to be walked. The second line contains a string of length n, with the ith character being of the string. The ith character of the string is G if the cow at the ith farm is a Guernsey, or H if the ith farm is a Holstein. So that's what this string is right down here, HHG. It's just telling us what cows are at what locations. The next n-1 lines, which remember the n-1 is how many paths there are. Next n-1 lines each contain 2 distinct integers, x and y, where X and Y are both between 1 and N, indicating that there is a road between farms X and Y. Let's scroll down a bit. I'm running out of room here. Okay, so I got my N here is 5, my M here is 5. This is the cow preferences. And then we have the 5 paths. This shows that farm 1 connects to farm 2, 2 to 3, 2 to 4, and 1 to 5. Let's go ahead and just draw that out real quick. So farm 1 connecting to farm 2, 2 connects to 3, 2 also connects to 4, and then 1 connects to 5. 5, 1, 2, 3, and 4. And then this string right here was giving us indication of what kind of milk is at each location. I'm going to do green for Guernsey. And let's see, so we got Guernsey at 1, 2, 3, and 5. And I'm going to do blue for Holstein. And Holstein was at 1, 2, and 4. And then the last 5 lines down here are the friends that are going to take a walk. So the first one shows that a friend is walking from 1 to 4. That's from here to here. And their preference is Holstein milk, and Holstein milk is blue. Okay, so let's see here. So then the next n minus 1 lines contain blah, blah, blah. The next m lines contain integers AI and BI, and the character CI, that's AI, BI, and CI. AI and BI are the endpoints of the path that I's visit, while CI is either Guernsey or Holstein, depending on whether they prefer Guernsey or Holstein. The output format is a binary string of length m with the ith character of the string being a 1 if the ith friend will be happy, or 0 otherwise. Okay, so let's just go ahead and run through this sample input, sample output. Okay, so the first person here, from farm 1 to farm 4, looking for Holstein milk. So they're going to start at farm 1, they're going to go to farm 2, they're going to go to farm 4, and in fact, all of those contain Holstein milk, so that's a 1 because he's happy. Number 2 is from 1 to 4 looking for Guernsey milk. Well, again, starting at 1, going to 2, going to 4, did not encounter any green for Guernsey milk, so that's a 0. That person is not happy. 1 to 3 looking for Guernsey milk. 1 to 2, 2 to 3, and we did find Guernsey milk there, so that's a 1. 1 to 3 looking for Holstein. We did find Holstein milk because that's at 1, so that's a 1 here. And then finally 5 to 5 looking for Holstein milk, and that's this one down here. And he's not happy because there's no Holstein milk there. So the big question is, how do you figure out what you have and haven't encountered on a path without having to actually walk through the path? I would recommend taking a couple minutes to get some pencil paper, draw this out, draw out a couple different maps, look at different ways that the maps can connect to each other, and try to think of how you can recognize or identify whether or not a certain path will contain all the different milk preferences without having to actually walk through all the nodes. So for example, the challenge is to figure out if I go from node 5 to node 3, what kind of pre-processing could I do that would let me simply look at 5 and look at 3 and then not have to actually find the path between them, and realize that in the path between them, I do have this section that I'm going to pass through that contains Holstein milk. All righty, let's clean this up a little bit. Okay, so the key to this is continuous groups. You want to try and put these into continuous groups. The big hint here is that there are only 2 kinds of milk. And if you could figure out a way to get all of the groups that are the same color and put them into sets together, like imagine this is like a regional map or something like that. If I could figure out how to put these into groups, then every single region, every single border crossing between these regions involves changing from one milk preference to another, from one milk availability to another. And then there's a border here as well. And since we only have 2 kinds of milk, then we are guaranteed that every single border crossing is going to take us from one kind to the other kind. And if a border crossing takes us from one kind to the other kind, that means that we are guaranteed to have access to both kinds. And then regardless of whatever the preference is, we know we've got whatever the person prefers. So if I were to name these regions, I don't know, Holstenia, Guernsenia, and then this one will be like Guerneton. So if I imagine these as like different regions, if I could get these grouped up and into different regions, then you know that if your starting nation is different than your ending nation, then you must have had access to both kinds of milk, no matter what. Because if I started at Holsteina and went to Guernsey or whatever, I've crossed a border, which means I've gone from Holstein milk to Guernsey milk. But notice this first one. This is both, what do I call it, Guernsey and Guernsey. Despite the fact that these both are Guernsey milk, because of the fact they're different nations, that means they must be separated by a region that has Holstein. So even though we don't know necessarily what path lies between Guernseyton and Guernsey, the fact that they are different regions, the fact that we put them in different nations means we're going to have to cross the border into some nation somewhere that has Holstein milk, and then we're guaranteed to have access to both. So let's kind of just look really briefly at the setup here. So I've got 1 to 4, 1 in Holstein. I've got 1 to 4, 1 in Guernsey. I've got 1 to 3, 1 in Guernsey. I've got 1 to 3, 1 in Holstein. And I've got 5 to 5, 1 in Holstein. And then the happy, I'll do true and false. True, false, true, true, false. All right, switch back over to blank here. Okay, my little scribbled notes here. So first person was going from 1 to 4 looking for Holstein. 1 is in Holsteina. 4 is also in Holsteina, which means we only had access to Holstein milk, but that person wanted Holstein milk. So we got a true, and that's fine. Next person is 1 to 4 looking for Guernsey milk. 1 to 4 starts and ends in Holsteina, and neither 1 nor 4 have any Guernsey milk because Holsteina has no Guernsey milk. So this is a false. That person's not happy. 1 to 3. 1 is here in Holsteina. 3 is in Guernsey. I should have made simpler names. Anyway, the fact that we have 2 different nations, we've gone from Holstein to Guernsey territory, means that we're going to have access to both kinds. So we don't even really care what letter he's looking for. We know that we have both regions. And if we have both regions, then it must be a true. 1 to 3 looking for Holstein. Same story. I've got a starting nation here and ending nation here that are different. It's in a different group. Therefore, we've crossed a border, which means we've had access to both kinds. And so then that's a true because we've had access to both kinds. And again, we don't even really care what they're looking for since we know we have access to both kinds of milk. Finally, looking for Holstein milk starting and ending in 5. Now, again, even though it's starting and ending on the same location, you've got the same path here. You're starting and ending in the same nation, which means you only have the milk of that nation. And in this case, it's Guernsey milk, but this person was looking for Holstein, so that's false. So the question then is, how do you get them into these groups? Let's roll this back a little bit. Go back to a simpler view. Oops. Okay, so we have these connected roads, and we're going to try and segment them off based on their milk preferences. So what you can do for this is, I mean, there's a million approaches. I like to set up an array when I have these kinds of problems, and each index of the array, so index 1, 2, 3, 4, and 5, has a number corresponding to what group it's in. And they're all going to start at group 0 because in the beginning, none of them are in a group. Then what I do is I start a, and you can use recursion or you can use an iterative process with some sort of a queue or a stack. I just do recursion because it's easy to do, but I have some sort of function, some sort of f of x. And what that f of x is going to do is it's going to it's going to first check to see whether or not the farm that I'm at is in a group. So for example, if I called f of 1, then I'm going to check farm 1 and see if it's in a group. If it's not in a group, then what I'm going to do is I'm going to place it into a group. And I need some sort of a group counter. You can pass that in with f or make that a global variable. So I have like f of x and then g for the group. So if I were to call 1 with group 1, then what I'm saying is I want to start from farm 1 and try to place it into group 1. So farm 1 gets placed into group 1 because it didn't have a group. I then check all of the neighbors of farm 1, which include farms 5 and 2. If any of them are found to have the same exact type of milk as what farm 1 has, then I'm going to recursively call on that farm. So in this case, because farm 2 also has Holstein milk, which is the same as I'm on farm 1, I'm recursing out, I'm looking, I see farm 2, which is a neighbor, also has Holstein milk. So I'm going to call f of 2, but passing the same group number. So then 2 is also going to get placed into group 1. Then from farm 2, we're going to look at all our neighbors. 1's already got a group number, so even if I call f of 1 with group 1, it's not going to do anything. 4 also is the same milk type, so I'm going to call f of 4, passing in group 1. And then farm 4 is going to be placed into group 1. Let's see. And then farm 4 is going to call f of 2, but f of 2 has already got a group, so it's not going to do anything. Already having a group is kind of a base case situation. And at that point, then I've called everything that's neighboring that's part of the continuous Holstein region. So I've got 1, 2, and 4 all in group 1. I'm going to try calling f of 2 with group 2, but that's already got a group, so that's going to be a base case. It's just going to return. I'll call f of 3 with group 3. And the fact that we don't have anything in group 2 doesn't really matter. We just need to have different numbers. So I call f of 3 with group 3. That doesn't have a group, so its group number gets set to 3. We check all neighboring regions to see if anything has the same color milk. The only neighbor I have is farm 2. Farm 2 is, however, a different color of milk, so I can't recurse on that. So that f is done. I would call f of 4 on 4, but I would hit my base case because 4 has a group already. And I would call f of 5 on 5. 5 doesn't have a group, so I'm going to put 5 into group 5. I'm going to check all neighboring regions, which only include this one area, to farm 1 to see whether or not any of them have Guernsey milk, because 5 has Guernsey milk. I don't have any neighbors with Guernsey milk, so I don't recurse any further, and that's the end of the function. Once I've done that, then what I have is an array where the index represents the farm number, and then the value in that index is going to represent what group that farm is in. So then I can just go back through my original problem set. Let me clean all this up here. Once I've done that, the process of placing these groups is going to happen essentially in linear time. Now, the reason this happens in linear time, despite the fact I'm doing what seems like a depth first search a total of n times, is that every farm can only be visited once. So what I have in my main area is a for loop that's going from 1 to 5 in this case. And I'm calling that recursive function with 1, 1, and then 2, 2. Essentially, I'm just calling f with I. Every single farm will get called at most one time, because what's going to happen is when I'm recursing through, for any given farm, I won't recursively call on neighbors if they don't have the same color of milk. And if I do recursively call on a neighbor that has the same color of milk, but that neighbor already has a farm, it's going to get rejected, which essentially means each one of these is only going to get processed once. Now, they may all check their neighbors once, but ultimately that's going to boil down to about a linear time, because every farm essentially gets processed one time and added to a group only one time. From there, then when I'm processing the M down here later, that's going to happen in linear time as well. So what I end up with essentially, instead of O of n times M, is I end up with O of n plus O of M, because I have the O of n work to build these groups, and then I have the O of M work because each one of these lookups is done in constant time. The way we're going to do that is 1 and 4. If I check 1 and 4, I look at farm 1 and farm 4. I see they're in the same group, which means in order to know whether or not I need Holstein milk, I just need to check to see whether or not farm 1 has Holstein milk, which I can look up in my original string here. 1 to 4 looking for Guernsey milk, again checking 1 and 4. I'll see that 1 and 4, let me move down a little bit, see if I can get this a little bit more visible. For 1 and 4 looking for Guernsey milk, I check groups 1 and group 4, farm 1 and farm 4, they're both in group 1, which means that I just have to check group 1 to see whether or not it has Guernsey milk. Since group 1 doesn't have Guernsey milk, since farm 1 doesn't have Guernsey milk, I know that group 1 doesn't have Guernsey milk. So this first one ended up being true, the second one's going to be false. 1 to 3 looking for Guernsey milk, 1 to 3. I've got in different groups. This one's group 1 and this one's group 3, which means I know I have both types of milk, so I can just print true without even having to look at what color this is. I just know that that's going to be true because I've got 2 different groups, so I must have 2 different milks, and there's only 2 kinds of milk, so I must have both of them. And that one's true as well. 1 to 3 looking for Holstein milk. Again, looking at 1 to 3, they're in different groups. They're in different groups means I have both types of milk. I don't even care what kind of milk he's looking for. I know that I have it because I've got both. Final one is 5 to 5 looking for Holstein. 5 to 5 are both in group 5. Since it's in the same group, starting endings in the same group, I just have to look and see what kind of milk I have in farm 5, which is right here. It's Guernsey, and I can check that in my original string. Since they were looking for Holstein, that means I don't have what I'm looking for, which means this person's not going to be happy. And that'll work for any size of map. So just as a real quick recap, essentially what you're doing is you will need to load this up into some sort of an adjacency list or adjacency matrix, some sort of thing that represents a graph. You will then recursively attempt to call a group placement function On each node, try to place each node into its own group number if you want to keep it simple, or you can try and keep track of how many groups you've done. But ultimately, what you need to do is generate an array where everything that is the same flavor that is connected will be placed into the same group. So I've got 1, 2, and 4 in the same group. 1, 2, and 4 were both in group 1. I've got farm 3 just ended up in group 3. Farm 5 ended up in group 5. And again, I don't have a group 2 or 4. It doesn't really matter. I just need to know where the different distinct groups are. Once we've got the distinct groups, you run through the array of connections here. And as you look here, you check to see if the starting and ending, excuse me. You check to see if the starting and the ending farm are in the exact same group. And if they're in the same group, that means that you just check in the string to see what type is the first farm. And whatever type the first farm is, the ending farm will be the same. And if that matches what you're looking for, then that's a true. If it doesn't, then it's a false. But if the groups are different, then we don't need to even worry ourselves about what type the person is looking for, because we know that if we've gone from one group to another, we've crossed a border between two neighbors that have different flavors of milk, which means that we must have had access to both kinds of milk. All right, that's the algorithm. Good luck coding it. I'll talk to you in the next one.